Welcome to a brief lecture on biomechanics. Today we're going to be talking about statically indeterminate systems. What do I mean by statically indeterminate systems? I mean basically a system if you have some body that is constrained in some way and you're applying forces to it. Oftentimes, if you draw free body diagrams of the system, you might be able to figure out the reactions. But for some systems, particularly systems that have multiple parts or multiple materials involved, we oftentimes won't necessarily be able to solve for all of the reaction forces and moments. And it turns out that if you make assumptions about the materials and how the materials could be deforming within the constraints applied to them, then you can get the extra equations you need to solve for unknowns. So we have these statically indeterminate systems. It turns out that we can break up types of statically indeterminate systems into various loading or deformation configurations. So let's make a chart. So this chart's going to have 4 rows and 4 columns. And the headings here. So first we'll talk about the type of loading. Basically what configuration it's going to be in. Then we'll talk about a relationship, if there's any kind of relationship between internal forces. Is there such a relationship? Is there a relationship between change in lengths of various components in the system? So is there a relationship between delta L's, between changes in lengths, or is there a relation between strains, various strains in various components of the systems? So based on the type of loading, we'll be able to say, hey, is there a relationship between internal forces? Is there a relationship between internal lengths? Are there multiple relationships? And basically by understanding if there's an extra relationship between internal forces or an extra relationship between internal lengths, then we'll be able to, that's where our extra equation to resolve unknowns is going to come from. So let's sketch out what these loading configurations could look like. So oftentimes these statically indeterminate problems come from beams or various bodies that are constrained in multiple places. So for example, maybe we have 2 rigid walls like this, and maybe there's a beam between them that's kind of divided into 2 parts, and a force is applied at some point in between them. So if we have a force applied at some point in between these 2 things, we might be interested in, hey, what are the reaction forces at each of these points, at each of these endpoints? But if it turns out if you just consider these as indeformable rigid bodies, then you won't end up with enough equations to solve for these reaction forces. There are other types of problems where maybe you have a thing, and rather than being constrained at 2 ends, maybe you have some chunk and then some other chunk coming out of it. Maybe part of it goes through, right? Maybe we have 2 different materials here and here and here. Maybe we're applying forces at the end. Or maybe we have one solid material here and then another solid material here, something like that. So we might have cases where we might be interested in, hey, what is like the overall deformation of the structure, or what are the separate deformations of these 2 parts here? Strictly speaking, this one actually wouldn't necessarily be statically indeterminate, but I'm sort of including it in the mixture just because it can be a type of loading configuration that you might run across. One type of system that is indeed statically determinate is, let's say we had a rigid support here, and we had and we were loading a chunk of one type of material here, but affixed to that one type of material was a different type of material here, and then we were applying some force to the end. You know, these materials in this case would be deforming together, but if the stiffnesses of these two materials are different, we might be interested in how much of the load is borne by one material as opposed to the other. And finally, there can be any number of complicated configurations, but maybe I might have a case like this, where let's say I had a couple of support wires that were holding some rigid beam like this, and I applied some force like this. So if we had just two of these wires, then we could sum forces and sum moments, and those would give us the equations we needed to basically figure out how much tension was in. If we only had two wires, that would give us enough, we would have enough information to figure out what was the tension in each of these wires. But if we had three wires, then we have an extra unknown because each of the tensions in the wires could be different, and we can sum forces in y, and we can sum moments. That gives us two equations, but we'd still have three unknown tensions in each of these wires. But if we know that maybe this beam on the bottom is rigid and it can sort of translate and rotate, then that can then sort of kinematic constraints and information about how stresses and strains are related in the wires can give us that last equation to resolve the unknowns. So what is the relationship between internal forces? Well, for this first loading configuration, the forces are related to F. They're related to our applied force, but not necessarily each other, right? We might have some internal force in this section, and we might have some different internal force in this section, maybe some internal normal force in this section, some internal normal force in this section, but they might be different from one another. If we look at the second configuration, if we took a slice of this beam right here and looked at the normal force transmitted internally through that, that would actually have to be the same as the normal force in this section, because basically if we sort of cut this, we'd have a force down and a force up. That would balance on this section. If we cut it here, we'd have a force down and a force up. It turns out it's the same force, or it's the same internal normal force throughout. And for this for this configuration, it would be equal to the force we get here. So we could and we could arrive at this by doing a free body diagram on some section of this rod that was sliced here, or some section of this rod that was sliced here. If we look at a configuration like this, there is a relationship between the internal forces. And if you imagined if we took a section of it and cut it, if we kind of cut it along this section here, we would still have this force F applied here, but we might have different internal loads within each section. So maybe we have an N for this one section here and an N for this section here. We would know they would need to sum to this force here, but they could be different from one another. So they're different within each section, but we know they sum to F. And similarly for this last section, we might not know straight away what all of these tensions are, but if we looked at a free body diagram for the this rod on the bottom, we know that there has to be three tensions. We don't necessarily know if they're equal to one another or not, but we know that all of them need to sum to F. So we know that all of these sum to equal our force here. But just from free body diagrams and summing vertical forces and moments, we don't necessarily know about the magnitudes yet. So the next thing we can ask about is there some relationship maybe between changes in lengths for each of these configurations. So for the first one, yeah, there actually is. So you can imagine if we originally were in this configuration for our beams, but after we applied our force, basically this line is going to move down a little bit to some new location. And it turns out that basically there's some increase in length of the top member and some decrease in length of the bottom member, right? So if this line moves down, basically whatever this lower one is, this needs to change in length equal and opposite to the change in length for this top one. So in this case, we might have something where maybe the change in length in segment 1 is equal to the negative of the change in length in segment 2. For this one over here, we're tugging some force down. This bottom segment increases in length. This top segment increases in length. So, maybe there's going to be some change in length overall that would be equal to the sum of the two changes in lengths. But we don't necessarily, just from looking at it overall, we don't necessarily know how much change in length there is in 1 or number 2 yet. For this one right here, where we have a beam that has like sort of a composite beam that's made of two materials, if the bottom stretches, basically they're both going to be stretching by the same amount. So in this case, delta L1 would need to be equal to delta L2. So in some ways, this is similar to this first one, where the changes in lengths need to be the same. Here, one increase in length needs to be the same as the decrease in length of the other. Here, they're both affixed to one another, so both increases in lengths are the same. Finally, for this last one, if this bottom beam is rigid, and it's really only these support wires that are deforming, then basically the bottom beam can rotate and translate. So there ends up being a sort of kinematics or geometry between the delta L's for wires. Right, so maybe originally they're all the same length, but then when they deform, the first one becomes longer, the second one becomes a little bit longer, and the third one becomes maybe least long if it's stretched in this way. So due to the geometry, this forms a trapezoid, and we can geometrically relate each of the increases in lengths. All right, so now let's ask ourselves, is there, maybe if there's some relationship between the changes in lengths, does that also mean there's some relationships between the normal strain experienced by each of these segments? So for this one, heck yeah, actually, they gotta have the same normal strain, right? If they start off with the same length and they have the same delta L's, so the original lengths are equal, and the delta L's are equal. So that implies that the strain must also be equal. That must also be equal for each. For something like this, the changes in length are equal. So the strain is derived from the changes in length. So it's related to these changes in length. But if this first one if the top segment is a lot shorter than the bottom segment, then even if the delta L's are equal, because the original lengths may or may not be equal, we can't say if are equal, but they are related to one another, and their relationship depends on these delta L's, but also on the original lengths. For this second one, the strains are also derived from changes in length, but in this case, the delta L's are even less related to one another than this one, so that's less helpful. For this one, and similarly for this one, the strains are derived from different delta L's for each wire. So what's the key takeaway? Well, if we have different loading conditions, in some cases, the internal forces are related to one another. For example, if we have a single force that's sort of transmitted first through one section and then through another section, and it's the same force in each section, which we would get if we cut it. We have some cases where the forces within each segment might be different, but there is some relationship between the delta L's. There might be some cases where not only are the delta L's equal or at least related to one another, but the strains are also equal because basically their initial lengths are equal and their changes in lengths are equal. And then we might have some cases that are pretty complicated. We might need to do some kinematics or some geometry to relate delta L's to one another. So the delta L's are related to one another, but not quite as in not quite as straightforward a way as like this or this. Why do we care about problems like these as bioengineers? Well, you can imagine that these types of loadings show up in all sorts of things, from prosthetics to the tissues even within our bodies to various medical devices. So for example, we might have a case like this where we have a compliant or soft material and then a rather stiff material like here, and actually the inside of our bones are kind of structured like this, where we have so-called cortical bone on the outside of our bones that are pretty stiff, and then cancellous bone on the inside. And it turns out that if we apply forces to our bones, the forces are shared unequally between the rather stiff cortical bone and the spongier cancellous bone on the inside. So if we're looking in bone biomechanics and we're applying forces, we can't just necessarily assume that that force is distributed evenly across the cross-sectional area, particularly when the material properties vary across the cross-section. We also might have cases like this where maybe we're designing a prosthesis for something, and maybe we have a transition from like tissue to a prosthesis over here, and if we're applying forces, we might be interested in what is the overall deformation of something. If part of that deformation occurs in the prosthesis and part of it occurs in the body, how much deformation do we get overall? So let's do an example problem. Let's imagine we had a post that was made of two materials. So let's say we have the ground right here, and we have some device that's rigidly attached to the ground, and it's sort of a cylinder, but it's a cylinder within a cylinder. So here we are, here's our cylinder, and it's a cylinder within a cylinder. So we're sort of viewing it as top as possible. You might encounter a geometry like this if you had a pipe within a pipe, or hard cortical bone on the outside and compliant cancellous bone on the inside. For this problem, let's just say that we have two different metals, and we have aluminum on the outside and brass on the inside. So we have aluminum on the outside and brass on the inside. And just to keep things simple, let's say we're just applying some downward force like this. And let's say we want to know, and this cylinder extends all the way to the bottom like this. And we want to know, hey, if I apply some force like this, there are going to be reactions between the floor and the aluminum part of this structural member and the brass part of this structural member. So I might be interested in what are the reactions, and we're going to consider the reactions, not just the reaction to the whole block in general, which would be pretty straightforward, right? Equal and opposite to F, but we want to split it in the various parts. So what part of the reaction is applied to the aluminum and what part is applied to the brass. So what will be important for determining how much of this load is borne by the aluminum on the outside and how much of the load is bared by the brass on the inside? And it turns out that there are a couple of factors that are important in determining those. So it turns out that the fraction of the load that each section bears depends on a couple of things. It depends on the cross-sectional area of each. So but it turns out that and you can imagine the one that has a larger cross-sectional area would be more likely to bear more of the load, but that's not the whole story. It's not, the cross-sectional areas are not just important, because you can imagine if the aluminum were very, very squishy and the brass were very, very stiff, then even if the brass had a smaller cross-sectional area than the aluminum, if it were a lot stiffer, it would still support more of that weight. So just imagine, instead of this being aluminum and brass, imagine we had a marshmallow and a rod of brass through that. If instead of having aluminum, we had a marshmallow, that marshmallow would bear hardly any of this load. So even if the marshmallow had more of the cross-sectional area, it's not necessarily going to be the one that bears more of the load. So what else is important is the stiffness. Is the stiffness of each material, aka the Young's modulus. So what's the key summary? The larger the cross-sectional area, the larger that one is likely to bear some of the force, but also the stiffer the material is, the more likely it is to bear a higher fraction of this overall force. So this sets us up for what are the things that we need to know about this problem in order to solve it. So let's say we're going to need to know the radius of this aluminum rod, the radius of the brass. The brass is in the middle, so we're going to need to know the radius of the brass, and we're going to also need to know the radius of the aluminum, which is the outer ring. So we're going to need to know these two radii. We're also going to need to know the stiffness of the brass and the stiffness of the aluminum as well. So we're going to need to know the force, the radii, the stiffnesses, in order to see how each of these factors affect how that force is divided and shared between the two parts of the material that are supporting that load. So what are these material properties, and what is the system geometry? So let's just give ourselves some numbers to work with. Let's say the radius of the aluminum is 1 centimeter. The radius of the let's say the radius of the aluminum is 2 centimeters. Let's say the radius of the brass is 1 centimeter. Let's say the stiffness of aluminum. This is something you could look up on the internet or in a textbook or something like that. The stiffness of aluminum is about 69 gigapascals, and the stiffness of brass is about 110 gigapascals. You might ask, hey, do we actually need to know information about this about the overall length? It turns out we don't need it. So for this problem, but for many other problems, you might need to know what that length is. All right, so these are the system parameters that we know. We anticipate that cross-sectional areas, which are of course related to the radii, and the stiffnesses of the material will affect the reaction forces, the part of the reaction force that's applied to the brass and the part of the reaction force that's applied to the aluminum. So, let's, if we're interested in reaction forces, well, we probably should start by drawing a free body diagram. So we have our free body diagram. I'm just going to kind of draw a side view of what it looks like. We're going to neglect weight. We're going to neglect weight for now. So in this case, we have force applied downward on the material, and we know there could be some reaction force applied to the aluminum. There could be some reaction force applied to the brass, and strictly speaking, this reaction force to the aluminum, I'm kind of drawing it here, but we would know it would sort of apply to the whole annulus shape of the aluminum right here. So, you know, it's applied, I'm drawing it here, but it's actually sort of applied to both sides because it's kind of the whole ring around. Strictly speaking, I guess to be complete, you know, because this is a connection that's sort of rigidly attached to the wall, you know, there could be some X reaction force, and I guess strictly speaking, there could be a reaction moment as well. We'll square these away in just a moment. So now we've done our free body diagram. Let's sum forces and moments to sort of see, hey, can we square away as much of these, as many of these as possible? So, all right, so we'll sum forces in X. All right, we'll sum forces in X. Well, actually, it just looks like the only force in X is our unknown reaction force. Just FYI, my knowns are going to be in blue, my unknowns are going to be in red, and things that I haven't really fully dealt with yet are going to be in black. So if we sum forces in X, well, really the only X force is this hypothetical X reaction force that we have here, and we set that equal to 0. We set it equal to 0 because we're assuming our system is static. If this were a dynamic system, we'd set it equal to ma. So the only X reaction force is Rx. We set it equal to 0 because it's static, so thus we conclude that Rx equals 0. So actually we didn't really have an X reaction force. Okie doke. So onward. All right, so let's sum forces in Y. All right, if we sum forces in Y, we have Ra, the part of the Y reaction force that's applied to the aluminum. We also have Rb, the part of the reaction force that's applied to the brass. And then we have minus F, because F is acting in the negative Y direction. I suppose I should add my X and Y axes here. And we set that equal to 0 because we're also dealing with statics. Okay, and then the last thing we can do is we can sum moments. And we can sum moments about, we'll just sum moments about the bottom. And we'll set our typical counterclockwise positive orientation. So if we sum moments about the bottom, these reaction forces don't really contribute anything to, a moment about the bottom. This Ra, I know this Ra is on this side, but we're sort of assuming it would be kind of equally applied across the whole annulus, so it would kind of cancel itself out. So it wouldn't apply any moments. Rb is sort of symmetrical about this bottom point as well, so that's not going to apply any moment. I guess we would have Mr, and F sort of goes through this point as well, so that's not going to apply any moment. And that too we set equal to 0 because it's static. So then we conclude actually there doesn't really need to be a reaction moment here as well. So no X reaction force, no reaction moment, 2 Y reaction forces, one part of it applied to the aluminum and one part of it applied to the brass. All right, so here we are. Some forces in X, some forces in Y, some moments about this particular point. And if we do all of those, we realize that we're left with one equation, but we still have two unknowns, RA and RB. So, and this is something that's characteristic of a lot of statically indeterminate problems. So statically indeterminate problems is, basically you can think of them as problems where once you do your FBD, you end up with more unknowns than you have equations, but you might be able to dig out some additional equations by considering the material properties and how the materials might be deforming together or at least related to one another. So what's the general workflow for these statically indeterminate problems? Well, you generally start with an FBD for the whole thing. And usually for these types of problems, once you do your FBD and you realize that you have more unknowns than you have equations for, you can kind of look at this general process. So what is the general process? Well, we have external forces. And external forces generally give us information about reactions. But it turns out these external forces alone don't give us quite enough information about the reactions to solve the problems. So it turns out that with information about reactions and external forces, that can at least give us information about internal forces. And for this problem, we're going to be mostly considering the normal internal forces that are transmitted through this system. So we have external forces. Those can at least give us some information about the reactions, but not all of them. It turns out that if we take our information about our external forces and our reactions, we can relate those to external forces. They still might be in terms of unknowns, though. So we have external forces, reactions. They give us information about internal forces, and that's where we're headed next. Let's look even a little bit beyond the next couple of steps that we'll be doing, talking about internal forces. The internal forces will give us information about stress, about stresses within each section. And of course, in addition to knowing about the internal forces, we'll also need information about the geometry. For example, the cross sections, right? Internal forces and geometry will give us information about stress. Stress is related to strain. For example, for normal loads, or I guess just in general due to material properties, if we're in the linear region of a linear elastic material, then the stress is proportional to the strain via the Young's modulus, and that's why we needed this information about stiffness earlier. So we'll be able to relate internal forces to stress via geometry. We'll be able to relate stress to strain via being in the linear region of the stress strain curve. And then we can relate strain to displacement. For some problems, we'll need to relate strain to displacement. So strain for normal strains would be equal to the change in length of something divided by the original length of something. So, hey, if these beams are deforming, right, if we're stretching them, the delta L's have got to be the same for both of them. The L naughts were the same, so we can relate strain to delta L's. It turns out that for these things, if they're being squashed like this, the strains actually need to be equal to one another. We'll get there in just a sec. But that means, but the stresses might be different. So we'll be able to sort of get at stress one way by talking about it in terms of displacements, strains, and the stress-strain relationship for linear elastic materials. We'll be able to get at stress from another direction by talking about external forces, reactions. We'll relate those to internal forces and stress. So we basically have a couple of different ways at getting at the center of these relationships. And once we get all the way to the center from both sides, then this will give us the one additional equation we need to solve for these unknowns. All right, so let's first work out these internal forces, because we need internal forces to start worrying about stress, right? So remember, if we're talking about normal stress, then normal stress would be equal to the normal load divided by the cross-sectional area of the part of the material that's bearing that normal load. So if we're going to get to stress, we first need to figure out normal loads. All right, so here we are. So to figure out normal internal loads, we can take our original system like this, and we can imagine cutting through and trying to figure out the normal loads. So if we take our system like this and cut it, like this, we on one side we have our reaction forces here, and then we know in each of these segments, in the one part of the segment that's aluminum, we know there's some normal load transmitted through this part, which we'll define with our outward positive orientation, and we'll call this NA. And then in the brass, there might be a different normal load, NB. So these are the forces that are transmitted through each segment. The aluminum part, which would be this side and this side, because it's really an annulus that goes all the way around. And then NB, which is the normal load in the brass part of this, which is through this. So here I've kind of drawn them together, but you could imagine really drawing these as two separate FBDs. One that's sort of one that's just sort of the aluminum part, and then one that's just sort of the brass part. And in which case, if we did those, then we would just have the two. We would just have these two things are basically acting. The two regions are basically acting kind of force-wise independent from one another. So if we did the aluminum, if we looked at the aluminum section, we would conclude that the normal force within the aluminum section must be equal to negative the reaction force at A. This would be I skipped a couple of steps, but this is what you get by summing forces in Y and setting that equal to 0. We could do the same thing in the brass, and we would conclude that the normal internal load in our brass is equal to minus the reaction force in the brass. And this is what you would get by summing forces in Y and setting that equal to 0. So where do we take this? Well, if we go back to our problem-solving strategy, now we have internal forces. These internal forces are in terms of reactions. But they're both still, it's all still unknowns at this point. But we can relate internal loads to stress via the geometry, and we know that our normal stress is equal to normal load divided by the cross-sectional area. So we can talk about stress, and if we do that, the stress in the aluminum part would be equal to, so we could maybe say the stress in our aluminum section would be equal to the normal force that's in the aluminum section divided by the cross-sectional area of the aluminum. But hey, wait a second. Can we put the cross-sectional area of aluminum? Can we put that in terms of knowns? Well, yeah, right? If we're thinking about the aluminum, the cross-section of the aluminum is the area of this donut, which is basically the area of this outer circle minus the area of the inner circle. So let's work that out. If we take it, so we still have Na in the numerator here, and the cross-sectional area of this aluminum donut shape would be pi times the radius of the aluminum squared minus the radius of the brass squared. Right? And if you distributed the pi, it would be pi r squared minus pi r squared. So it's the outer circle minus the inner circle. We can also talk about the stress in the brass. And that would be equal to the normal load, within the brass divided by the cross-sectional area of the brass. And this is, of course, the cross-sectional area of the aluminum. So that's going to be ND divided by, and that's just going to be pi RB squared. Okay, all right, so now we have stresses in terms of normal loads, but ultimately what we wanted was to figure out the reaction forces, or these reaction forces, so we can plug in these normal loads in terms of our reaction forces to get closer towards a relationship between what we're actually trying to solve for, which is these reaction forces. So in this case, it'd be minus RA when I sub in that, and here we have minus RB over, and they'd both be over so there we are. All right, so if we go back to our general kind of flow of relationships and information, let's now try to work from this side. So we'll work from the displacements to the strains back to the stresses. And with the idea is if we can get stresses in terms of something else, then maybe we can kind of plug in these expressions for stresses and try to get another relationship between our reaction forces. So if we work at it from the other side, if we think about how this block, or how this cylinder with a cylinder within a cylinder is going to deform, you know, if I take it and I stretch it, both parts need to kind of stretch together, right? If they stretch, they're both going to stretch the same amount. So what does this mean, right? If I apply a little bit of force, it stretches. If I apply more force, they're stretching, but they're both going to be stretching together. Similarly, if I applied forces inwards, if they compress, they're both going to compress together, right? So similarly, if I have applied forces inward, if they compress, you know, they're both going to compress. They're both going to compress together. They're in it together. So, so what does this mean? This basically means our delta L's must be equal in both the aluminum section and the brass section. But hey, wait a second. If we sort of think about this thing in the undeformed state, right? If we think about this before any deformation occurred, they both had the same original length too. So L naughts, right? The original lengths, the undeformed lengths are equal, just because they both started with the same length. So if the delta L's are equal and the L naughts are equal, well, if we recall, remember normal strain is equal to delta L over L naught. If the L naughts are equal and the delta L's are equal, we don't necessarily know what these delta L's are yet, right? They're still unknowns. Maybe I should have drawn them in red because they're kind of unknown. But if the L naughts are equal, we don't know exactly what the delta L's are, but we know that they must be equal to one another. What does this mean? This means that the strain in the brass must be equal to the strain in the aluminum, because the delta L in the aluminum over L naught must be equal to the delta L in brass divided by L naught. So because these L naughts are the same and the delta L's are the same, the strains must also be the same. So where does that leave us? Well, so we said, okay, there's a relationship between the displacements, basically because the delta L's need to be the same. It turns out because the L naughts are the same, that also means that the strains are the same in the two. Well, hey, we have a relationship between stress and strain, and they're related via the Young's modulus. So what does that mean? This basically means the stress in the aluminum is equal to, I'll put this in terms of the stress in the aluminum is equal to the strain in the aluminum times the Young's modulus of aluminum. And if we recall, the Young's modulus of aluminum, right? Young's modulus of aluminum is some property of the material that we can know. So our stress in aluminum, so stress is equal to strain times Young's modulus, right? And that's just a product of, if you plotted stress versus strain and you had some slope, the slope of that curve would be the Young's modulus. So this is just the algebraic version of this graph. Similarly, the stress in the brass, that's going to be equal to the strain in the brass times the Young's modulus in the brass. So how does this help us? Well, from this earlier thing, we know that these two, we don't necessarily know what they are, but they're equal to one another. So what does that mean? Well, this basically means that, so we can just say, rather than talking about the strain in the brass and the strain in the aluminum, we can maybe just call this just a single unknown, just the strain. So what does this mean? This means the stress in the aluminum is equal to the strain that occurs in either section times the stiffness of aluminum. And the stress that's in the brass is equal to the strain that's in either or both sections times the stiffness of brass. These were both knowns that we had at the beginning, right? This is our stiffness of brass. So what does this mean? Well, we basically have stresses over here that were put in terms of our reaction forces, and equations for stress here and here that are put in terms of strain. So what does that mean? Well, this means we have a system of equations and unknowns that we can solve. So what am I going to do? I'm going to take these equations up here and put them over here. So here I have my stress in the aluminum section, and I can set that equal to the stress formulated in terms of strain in the aluminum section. So that's going to be strain times the modulus of aluminum. And I can set the stress as formulated in terms of reaction forces in cross-sectional area. I can set that equal to the strain times the stiffness brass. So now if we look at what we have here, what do we have? Well, we have two equations and three unknowns, right? RA, RB, and strain. But if we tie in the equation that we had earlier, RA plus RB minus F equals 0, what do we have? We have 1, 2 equations, 1, 2, 3 equations, and 3 unknowns. Yeah, we can solve this. All right, so let's square away this algebra, right? It's just algebra at this point. We have 3 equations and 3 unknowns. So first what I'm going to do is I'm going to solve each of these for strain and then set them equal to one another. So what do we get when we do that? Well, if we divide this both sides of this equation by the modulus of aluminum, then we get minus the reaction force at A divided by pi RA squared minus RB squared times the stiffness of aluminum is equal to strain, which must also be equal to whatever we get if we divide both sides of this by the stiffness of brass, RB divided by pi RB squared times the stiffness of brass. Great. So we can solve this for either for RA or RB. I guess it doesn't really matter. So what do we get when we do that? I guess we could say RA is equal to RB times EA over EB. For RB squared, right? I canceled the pi's and I canceled the minus signs on both sides. I guess I could simplify this a little bit, and I could get it to RB. All right, so there we are. We now have RA in terms of RB. We can sub that into this equation here. What do we get when we do that? We get RB and then we still have this plus RB here. And let's bring the minus F over to the side. So that's equal to F. So you can imagine, what do I have here? Well, I could factor out this RB, divide both sides by that whole big slew of constants that's over there, and then I could get RB in terms of knowns. All right, so I have RB, and then that would be equal to F divided by, right, so if I factor out an RB from this, that is this thing plus 1. So it's EA. Oops, sorry, I'm off the screen. It's F divided by this whole big slew of constants, so it's EA over EB, RA, RB squared minus 1. This whole thing plus 1 from factoring out the RB over this whole thing. And what does that mean? We now have RB entirely in terms of knowns. I could leave that up to you to basically plug in these values here to get it. And we could get RB entirely in terms of knowns. And then once we have RB entirely in terms of knowns, we could just plug that in real quick here and solve for our RA. Woohoo! And then we could pat ourselves on the back for having done such a good job. So what's the key thing here? Well, oftentimes once we get to the end of a problem like this, we could do a units check. So let's do our units check here. So you have a whole bunch of stuff. So F, that's going to be in terms of newtons. We have EA over EB, so that's going to be newtons per square meter, but we're going to divide it by basically something that has the same units, so that's newtons per square meter. We're multiplying that, so RA over RB, that's going to be meters over meters squared minus 1 plus 1. Well, this is okay, right? We have something without units, and the meters over meter cancel. When you square something, well, that doesn't have units, so something without units squared, that's fine, right? So this whole thing's okay. These units cancel, so this whole thing doesn't have units, and 1 doesn't have units here too. Then we're left with just newtons in the numerator, the newtons associated with this F here, and this RB, well, that's a reaction force, and that's in newtons as well. So, okay, great. So that means, what does that mean? Well, that means that our units check lines up, so we're getting a sane answer. Let's do another sanity check. So what happens if RB, which is the radius of the brass part, right? Remember, RB is this part, RA is this part. What happens as RB starts to approach RA? Well, if RB starts to approach RA, then this term here starts to approach 1. If this term gets very close to 1, then this whole term basically goes away. And what does that mean? That means this whole term basically gets F. So what does that mean? That means as the radius of the brass starts to approach basically the whole radius of the whole area of this entire thing, then basically all of the force gets borne by the part of that's brass. And that makes sense too, right? If brass is basically making up the entire cylinder, then the reaction force that the brass bears is going to be basically the entirety of F. So that's another sanity check that this makes sense. Thank you.